Okay, clapping. Am I running low? See, this is the problem. You gotta tell me when it's low. Otherwise, I don't know. It's like, do any of you put back empty cereal boxes for your mom? You pull out and you're like, I remember my siblings like, there's like still two. Okay, everybody. There's some more in the back, Zach. They're just a little deformed because they got like, they rolled around in a car, but they're fine. Oh, they just weren't in like concealed case, so they're a little like. Okay, give me your attention here, everybody. Obviously, understanding is the main priority, so I'm not going to rush past understanding, but a lot of you are being dismissed today at 12 o'clock for honor roll and high honor roll award. So you'll know if you're one of those because I have a little paper for you, but my papers are quite thick, which means it's a lot of you. So I want to try to get through the lesson as much as possible before that point. So I want to try to get through it as much as we can so that, yes, even though I'm filming it, I don't want the majority of you to have to go and like finish something on your own. Okay? So let's jump into themes once again so we try to get through this. Okay? Alright, so today's lesson here, everybody. So in part of getting through this, right, we gotta be focused. So right now we're in the, my lights came in today, so next time you come, we'll have them set up. Okay, but right now we're in level 3, which means class discussion, so one talking at a time. So if I'm talking, you're not. If I've called on someone else to speak, you're still not. Okay? Alright, so today's focus is all about solutions. So keep in mind our unit that we've been doing, we had solids, then liquids, then gases. Today we're talking about solutions. Now a solution isn't another state of matter. It's a combination of two matters together, but it's kind of its own classification. So a solution is what you get when you mix a solid and it dissolves in the liquid. Keyword, it has to dissolve. If it doesn't dissolve, then you just have a liquid and a solid sitting together. Hence, if I put wax in water, the wax doesn't dissolve, it just is sitting in the water, so we wouldn't call that a solution. The key component of it being a solution is it dissolves, and it really now looks like one thing. Okay, so we often use the word homogeneous when we're describing a solution. It looks like one thing. Great example is salt water, right? Like if I have salt water, it looks like a pure substance, but it's actually not. It's made up of two components. Okay, now they can be colored. This is a homogeneous mixture that's colored. I haven't stirred it very well, so there's some solids sitting at the bottom. But you can have it colored. That doesn't make it not a solution. Okay, so today's all about solutions. Our objective is I can understand solutions from all three sides of our triangle. So from the top side of our triangle with our eyes, understand solution is recognizing a lot of times solutions look like water. Now, it doesn't have to be with water. You can have solutions in other substances, but always assume water unless told otherwise. Like the problem would say it's a solution in alcohol if it wasn't in water. But normally we're going to deal with aqueous solutions. Okay? We're going to first start by going to the symbolic side of how do we measure and represent different types of solutions. This is known through a property known as molarity. You have a little box there somewhere on your notes. Okay, this is the equation for molarity. Molarity is the relationship, hence my little picture up there, of how many moles in 1 liter. So a molarity is represented by how many moles in a liter. Okay? It's represented by a capital M. So if I have a solution, it would say like, oh, this solution is a 12 molar solution. Its molarity is 12. Okay? Or you could have, once again, any different number, a molarity of 1, right? But capital M represents there's that many moles in relation to 1 liter, okay, of water. Right? So it's I've dissolved. So if it's a 1 molar solution of salt, so here's like an NaCl crystal. Let's pretend this represents 1 mole. If I take this 1 mole and dissolve it, doesn't fit, but go with my analogy here, in 1 liter of water, Stir it around, I have a 1 molar solution. Okay? Now, with this idea of molarity, for a smiley face starting off today, don't say it out loud. Which one of these is higher concentrated? Point up to 12 or point down to 1? Which one is a higher concentrated solution? Let's just connect the vocabulary word here, concentrated and molarity. So is 12 more concentrated or 1 more concentrated? Show me what you think. If you're pointing up, have a smiley face. So the idea is this is saying taking 12 of these and putting it in one, versus this is just taking 1 of these and putting it in. So it'd be much more concentrated amount. So the number makes sense to what it represents. Okay? All right, let's try a problem here of calculating molarity. Now, with this problem says we want to calculate the molarity of a solution made by dissolving 23.4 grams of sodium sulfate, gives us the molar mass, which is handy, and enough water to form 125 milliliters of solution. The goal here is calculating the molarity. Okay, so I'm going to write that equation down again. So molarity equals mole per liter. Okay? So in the end, molarity is like density where it's 2 units coming together. So we need to take what is given and get them into these 2 units so we can bring them together. So what information is given that I can use to get to moles? Grams. Good, so take your 23.4 grams of our sodium sulfate. And I'm going to convert that into moles. So conversions follow, grams is here. So gram is on the bottom, moles on top. What do I use to get me there? Good, periodic table, but they actually gave it to us. We don't have to do the work, but otherwise periodic table would give it to us. So they told us it has a molar mass of 142, so we don't have to add it up ourselves. Okay, so then we do 23.4 divided by 142, and I got an answer of 0.165 moles. Questions on that? Okay, so that's going to give me the top part of my fraction here, 0.165 moles. Now the bottom needs to be liters. What value does my problem give me? Conversion between milliliter and a liter is 1,000 of a difference. So you divide by 1,000 to convert it to a liter, which is the same as just 1, 2, 3. So 0.125. Okay, so it's like you have conversions, but then you bring them together, moles over liters, divide that in your calculator, and I got a molarity of 1.32 is my molarity. Unit-wise, you can just write capital M, because that is molarity. If you want, you could also, this is the same thing as writing 1.32 mole over liter. They're one and the same. Questions on that? How I did it, where number came from? Okay, we're going to try another problem in a second, but I want to point out 2 things about this problem. First off, this problem, oh, maybe I should just get rid of it. I do it every year, and I say this every year. This is a very ridiculous problem. Because this is not something you ever do in real life. You're never just going to take a random amount of salt, dump it in a random amount of liquid, and be like, I wonder what its molarity is. I mean, maybe you guys would. Like, as a chemist, like, it's pointless. You always are making a molarity for a purpose, right? You're like, okay, for this experiment, I need a 2 molar solution, or I need a 0.5 molar solution. Like, the molarity is like a set thing you need. It's not like a random value. So that's why this one, first off, is a little weird because it's like calculating just this random number. But the other thing I do want to point out in the process of making it, okay, so this is going to connect the symbolic to like what we would see with our eyes, okay, is this phrase right here. Notice right there at the end, and maybe underline it here, it says, we want to know how much in enough water to form. Any ideas by raising hand? Why did they phrase it that way? Like visualizing what's happening. happening. Yeah, Lily.
Is it so that when you add the sodium sulfate, it doesn't go over the 105?
Perfect, Lily. Have some ideas for that. So when you make a molarity, you don't want to measure the liquid and the solid separate and then pour them together, because the solid takes up space. And we want the total volume to be this. So the way you make it is, I always think of it as a water sandwich. So you pour in a little bit of water, then dump in your salt. That just helps it from like sticking at the bottom. Then add the rest of the water you need until you get to the mark of your measurement. And that's why you're always going to use what's known as a volumetric flask, which is these types of shapes, okay, versus a graduated cylinder. So graduated cylinders are great for measuring volume because they give you lots of different markings. So you can measure all sorts of things, anything from 1 mil to 50 mils, and in between I can measure on this. A volumetric flask is designed to measure one volume and one volume only, but it measures it with the most accuracy possible. When I measure to this line, it means I am only off by less than plus or minus 0.1 of a milliliter. But it only measures 500 mils. So I'll come around, there's a faint little gray silver line right where my finger is. So that's the only line on here because it only measures 500 mils. Same thing on like my smaller one, you can see on the neck of it. So they are designed to measure very good precision, but only to one thing. A graduated cylinder has a lot of options for you, but it has a plus or minus of 5 milliliters.
Oh, that's a lot.
Yeah, so that means like you may think you measured 40 mils, but you could be anywhere between 35 and 45. And so the accuracy is not as good. So when you're trying to create something, you want the most precision possible, okay? So we'll kind of talk more about those, but just getting you familiar with some glassware names, okay? All right, let's try this problem. So this one's way more applicable to like what you would do in a lab setting. The student wants to prepare 2 liters of a 0.1 molar solution. So you know how much volume you want to make, and I know I want it to be this concentration. Our question is, how much do I need to weigh out to make that happen? So we're still using the same equation, it's just now the difference is what we're trying to find. So I'm going to keep the same equation, but I'm going to plug in what is given. So what information is given this time? So liters is given, so I'm going to plug that in the bottom. So we have 2.00 liters. What else is given?
Molarity.
The molarity. Now notice that word molar, if you want to label it, molar is just how you can like talk about molarity. By saying it's a 0.1 molar solution, that refers to its molarity. You don't really say like 0.1 molarity solution. I don't know, just English language, I guess. Okay, so we know M already, so it's what, 0.100 M? So what we don't know this time is the moles. So we're trying to figure out how many moles do I need to make this solution. Okay? All right, using algebra, how do I get x by itself? Good, so I'm going to multiply 2 to the other side. So x is going to equal 0.200 moles. Questions so far? Okay. The question though says a proper procedure to weigh out. Can I weigh out moles directly? No. So I got to go to grams. Okay, so for every 1 mole of, what's our thing, KiO3. And once again, they were very nice and gave us the molar mass already, so I don't have to find it. All right, so this is going to convert it from moles into grams. So when I type that in, you get 42.8 grams of KiO3. Questions on either of these molarity questions? So homework 3.7 is just a bunch of molarity questions because there's a lot of different ways it can be asked, but in the end you're just still using this, finding the unknown, and then possibly converting units as needed. Any questions so far? Okay, let's take a look at the next section here. So with the idea of a solution, so molarity once again comes to our symbolic, the mathematical side of how to calculate it. We're going to shift now a little bit to the molecular side of what's going on, particularly the difference between ionics and covalence. Because both of them can dissolve, but they can do two different things at the molecular level. And because of it, one of them is classified as an electrolyte, and the other is not. Now, we actually dealt with electrolytes before, but we didn't really name them that. When we did our unknown lab and you used the little electricity probe, and you stuck it in water, remember the lights would light up red or green if it was conductive, okay? This is distilled water. Does distilled water conduct electricity?
No.
Why not? Lily?
Because the electricity only moves through things that are like dissolved or like in the water. It doesn't actually move the water itself.
Yeah, so electricity are electrons, everybody, okay? So that's all electricity is flowing electrons. If something's going to conduct electricity, those electrons have to keep flowing, right? I think of it as a crowd surf, right? That something has to keep passing the electrons through, and that will conduct electricity. Pure distilled water, straight up H2O, has nothing that will pass the electrons. But some things, once dissolved in the water, then create the ability of electrons to flow. Now, the reason why we name them electrolytes is because they literally conduct electricity. So this right here is a light bulb, right? Now notice it's plugged in, okay? I'm not generating electricity from this beaker, it's just continuing the flow. So right now it's an open circuit, right, with these holes right here, and so it doesn't light up because the circuit's not connected. If what I put it in conducts electricity, then it will continue the flow and light up the bulb. So as long as my distilled water isn't expired, yep, then it shouldn't light up.
Water can expire?
Well, just like because the container starts like dissolve, like the plastic can get into it and like stuff like that. But what I have right here is I've dissolved copper sulfate, which is an ionic compound, in water. Okay, so this is what it looks like as a solid, so it's a pretty green compound.
If you used tap water, would it light up?
What do you think?
Wow. Depending on what's in the tap water.
Let's try. So Levi asked if tap water would conduct, so let's test his experiment question. Right, so we can see with the ionic substance, right, good conductive, hence why they're called electrolytes. Once again, in case you haven't recognized, like Gatorade didn't come up with the word electrolyte, like it's a scientific word that they just use, excuse me, because they have electrolytes in them, right? So if I poured Gatorade in a beaker and tested it, it would light up. And electrolytes are what our body needs because our body sends electrical signals, right? If you don't have enough electrolytes, then you get muscle cramps because those electrical signals can't travel as they should. So that's why your body needs electrolytes. You can get electrolytes from anything that has salts in it. It doesn't have to be Gatorade. Okay, so here's our tap water test.
Wow.
So not really. Often it does conduct somewhat. It must not be strong enough this time because there are ions in there, but ours must not be strong enough.
So it just depends on like what's in it.
Yeah, and it doesn't mean it's bad, like if it does, right? Because electrolytes are good for you. So yeah, it just kind of depends on like maybe how much filtration the water goes through or whatnot. So
Flint, Michigan. This is how these are.
yeah.
You should go to Flint, Michigan and see if their water is conductive.
What's in
Really bad tap water.
Oh. Alright.
Like extremely dirty.
That'd be interesting to have like all those samples.
It's like a big news a while ago.
Oh, okay, yeah, I know you're talking about now. Okay, so with this idea of ionics, okay, because they are electrolytes, it's that the molecules themselves get broken up. Now, keep in mind when we're talking about capital M, excuse me, capital M is moles per liter. Moles is a counting thing by the group. If the group is one thing, it counts as 1 mole. But if it breaks up into 2 things, so NaCl is like this, but once I drop it in water, it becomes this. This still counts as 1. Okay? So 1 mole, this is 1 mole, but this is still 1 mole. So if the molarity of NaCl is 1, when it breaks up, the molarity of just Na is still 1. The molarity doesn't cut in half because it didn't cut the sodium in half. The molecule broke in half. Same thing for Cl, it's still just 1. Because the ratio was 1 molecule became 1 in 1. So keep in mind, this is the idea that moles are not additive. Because this says 1 equals 1 plus 1, which does not work in actual math. Okay? All right. Questions on that so far? Now, for other ionic things that look a little more complicated, you still take the same idea, but you have to consider how it's going to break up. Okay? So if you look at the molecule, and the molecule is made up of more than just 2 things. Okay, so in this case, we have sodium, we have sulfur, we have oxygen, lots of capital letters. Okay? If it's made up of more than 2 things, you still know, because it's ionic, that 1 part is positive and 1 part is negative, because that's how ionics work. So to define the dividing line is you draw it right after the metal. So everyone, do you guys remember how to determine where metals are on the table? Left of the staircase. Okay, so if I look at this, it's the metal. It's always going to be the metal because metals are always listed first. But I know this is the metal, so I'm going to draw my line right here. So this tells me that this is the positive thing, and this is the negative thing. Now, on the negative side, you'll notice it's more than 1 capital letter. Right? This is not 1 element, it's multiple elements. Okay? Is sulfur a metal or a non-metal? A non-metal. Is oxygen a metal or a non-metal? What type of bond is described when 2 non-metals bond? Covalent. So this is one of our polyatomic ions that we addressed in Unit 2 a little bit. We'll keep seeing them a lot as we go. They're the elements that are covalently bonded together, but then it's ionically bonded with sodium. Covalent things don't break up any smaller in water. So this is a big thing, but we're going to treat it as if it's this 1 green circle. That 1 green circle represents SO4. If there were more of them, then there would be a number outside of a parenthesis. That would tell me you have multiple of them. Okay? So to model this molecule, this one would look like, because I do have, so notice the little 2 here. Okay, so I have 2 NAs and 1 SO4. So in a sense, that's kind of what it would look like. So when this breaks up in water, it's going to break up as much as it can. So what would be the molarity of the Na plus now? Twice as much. So it would have a molarity of 2 molar here, but still just 1 molar for that. Yep, so now 1 equals 2 plus 1. Once again, moles are not an additive thing because you're just counting them in groups or as separate pieces. What questions do we have about this? Yes, one more.
So how do you know that like
Because of this.
Oh, I see.
Yeah, good question though. Yeah. Yeah, so the metals will always break up as much as possible. Okay, let's try this, because this will help us know if we for sure got it. I'm going to write 3, I didn't put them in our notes, I just thought of these last period, but I think it will help. I'm going to write 2 example problems. As a table, write your answer on your boogie board, I'll get you one if you're missing it, for some smiley faces. Okay, so what I want you to do is I'm going to give you the overall compound, its molarity, you're going to tell me what is going to be the molarity of the pieces it breaks up into. Okay, so the first one, let's do... Okay. Fun fact, we'll keep seeing little S's Indicate it's a solid substance. So if you've seen those, and you're like, I wonder what those are. It's just telling you the state of it. If it's an L, it's a liquid. G's for gas. Okay, so let's say this is a 1 molar solution. You're going to tell me what is the molarity of the lithium ion, and then what is going to be the molarity of the oxygen. Okay, so there's problem number 1 to do on your board, and then problem number 2. Let's do a 1 molar solution of calcium nitrate.
Wait, is it LiO2?
LIOS. I meant to do that.
Okay, talk as a table. I'll give you 3 minutes.
On the top. I thought it was his gun.
So nitrogen bonds with oxygen. This is in it, that's they're both negatively charged. All right, you got 15 seconds to get your answer down if it's not. Okay, very good. We're mostly all there. I just knocked them out on camera. Now they're just gonna watch that table work. Sorry, people. Okay, so you should have, so you can have a smiley face for each solution you got correctly, so up to 2 smileys. So you should have 2 and 1, and then 1 and 2. Okay, does that make a little more sense? I know it feels a little weird because of what moles are, but we'll do that. Okay, the next thing we're going to look at here is another equation. So one way we can make a molarity is by dissolving, right? I take a solid, I dissolve it in the liquid. The other way you can make a molarity is by taking a higher concentrated value, and I can go through a process of what's known as dilution to make a lower concentrated one from that higher stock. So instead of taking a solid, I can just add water to something highly concentrated with enough to bring it down to where I want. The idea of diluting something here, where'd my sample go? Oh, here you are. Okay, so like this right here is a solution already made. It's a 1 molar, I just pulled it on my cupboards. It's a 1 molar solution of copper sulfate. Okay, so I could use this if I wanted to make it a less concentrated solution, so like let's say a 0.1, I could use this to get me there instead of using a solid substance. Okay, the idea is if I just pour water to this, right, so remember molarity, what does molarity equal again? Okay, so if I add water to this, which of these factors am I changing? Just the liters. So in the end, the moles before will equal the moles at the end. That's how the math works, is because you're not changing how much is in there, you're just adding more water so it's more spread out now. Right? That's what it means to be diluted, is there's more space compared to how there was before. So the equation for this is you take molarity 1 times volume 1 should always be proportionate to molarity to volume 2. The reason why, so this is the equation, here's like the reason why it works, because molarity is moles per liter. What's the unit for volume? A liter. So if I have moles per liter, timesing it by a liter, it just says moles. And so that's the idea, is that moles will equal the moles. Right, but the molarity changes because molarity is based on how much volume you have. Now, I don't know why they do this, but this equation, this one right here, if you want to make an extra note, is not on your formula sheet. I don't know why. They give you a formula sheet, but there's like 4 equations this year we'll learn that they don't put on there. I don't know why they don't just put it on there. Once again, you can kind of get it just from the fact, if you remember this idea that moles have to be equal, but just know that this one's not there. Molarity's on there. You don't have to memorize the molarity equation, but this one's not. Okay? All right, let's try a problem with it. So this one says we want to prepare 250 mils of a 0.1 molar copper sulfate. So I'm just going to move this down a little bit so I can write on it better. Okay? By diluting a stock solution containing 1 molar copper sulfate. So just like what I have here. I have a 1 molar. I want to know how much of this do I need so that when I dilute it down, I can get this molarity and this volume. Now with a dilution, the biggest thing is just keeping them grouped up the right way. It doesn't really matter which one you call 1 or which one you call 2, as long as you've paired them how they should be paired. So I'm going to say, I like to always say the thing I'm making is my M2. So label this here, this one is going to be my V2, because I want to make that volume. This right here is going to be my M2, because that's the molarity I want to make. The molarity that I'm starting with is given here, so this is going to be my M1. And so then the one piece that's missing is how much of that volume. Okay, so I kind of just label my different pieces, so now let's plug into the equation. So we have M1, which is 1.00 M. Okay, so this is M1. We need to times it by V1, which is our unknown, so I'm going to keep it as a letter. Equals M2V2. So the new molarity I want is 0.1 with a volume of 250 mils. Now, because it's a proportionate equation, you don't actually have to convert to liters because you're proportionate. It means our answer will be in milliliters, but that's just fine. Okay? So here's my unknown. This is your x. So to get x by itself, divide by 1 plug that into your calculator and you get V1 equals 25 milliliters. So I need 25 milliliters of our 1 molar copper sulfate solution. Questions on how I did that? Yeah, Emily, what is it? Great question. So what it means is, here's my 1 molar. I'm going to measure out 25 mils of this. All right, so I've used this to measure out 25. I then would take that 25, I'd put it in a 250 milliliter flask. Pretend this is 250 milliliters. I'd pour this in and then add the rest water. Does that make sense? Yeah, good question, because it kind of has like pieces of how it actually would be performed in the end. Other questions on this idea of a dilution? Okay, I'm going to skip. The next question was just a practice one to do, but to try to get us through this before 7 weeks, we're going to skip it for now. Because it's not anything new, it's just practicing it. We'll come back to it for those that do under it at the end. But skip to this part here so we get our last one.
Obviously.
Obviously not, that's what I'm saying.
Why are you just doing it to the outside?
Electrolyte.
Okay, so coming back to this idea, so now we're going back to the molecular side of visualizing these things. Okay? With the idea, once again, you need to understand there's a difference. Not everything that dissolves is an electrolyte. I should have done it because I have sugar. But if I had a beaker here of sugar water does not conduct electricity, but sugar does dissolve in water. So there's a difference between what we call dissolving and ionizing. Ionizing refers to the idea of it's electrolyte now. Dissolving just means you can't see it with your eyes. Okay? Once again, the big dividing line is the difference between ionics and covalents. Right? That ionics are always electrolytes. Covalents are not. But they both can dissolve. So we're going to draw a picture in that graph right below to kind of understand the difference of why. Why do ionics conduct electricity, but sugar doesn't, even though they both dissolve? Okay? Sorry, that word right there, if you can't read, is electrolyte. Sometimes right in that spot, that's always hard to read. I'm going to figure out a way to like get rid of that bar, I don't know. Okay. Is everyone okay if I go to the next screen? Okay, so we're going to draw 2 pictures at the molecular view of what's going on in these solutions. So the first one we're going to do is sodium sulfate. Okay, I'm going to write down here, because I can't write up there, but what I write right here, put in that box. Okay, so sodium sulfate, once again, little s is indicating it's a solid. We're going to dissolve it in water, so I'm going to put H2O above the arrow. The reason why I'm putting it above the arrow is it's not a chemical reaction. These things aren't like bonding with each other chemically, but they are going to be mixing, so I want to show what's coming. Okay, so when this gets put into water, as we saw before, it separates into the pieces of 2 Na pluses and 1 SO4 2 minus. Once again, the 2 there is because it broke apart, just like how the molarity was changing. Now, these aren't classified as solids anymore because they have dissolved. So we don't put little s, we actually now put the symbol AQ. Stands for aqueous. So aqueous is a symbol for saying, hey, this is a solid dissolved in water. That is very different from calling it a liquid. A liquid would indicate that this substance has melted. And it's not melted, it's just dissolved. Yeah, Levi.
Why is it 2 minus with SO4?
So there's a few ways you can think about it. For now, so like I said, it's one of our polyatomics. And the polyatomics just have a set charge. So one is you can kind of go the reverse of, it has to be balanced to 0 here. So sodium has a +1 charge because of its valence electrons, right?
Oh.
And so if there were 2 of them in the formula, for it to be 0, it had to be that. You also, for now, because I'm not going to make you memorize them, I gave you a polyatomic chart. It's in your notes, but they're also on the back of some of these. It's in Unit 2 is where this chart is in your notes. But you can also just use this. If you find SO4 on here, you see it's under the 2 minus column. But great question, Levi. I have a smiley face for that, because I'm sure others are confused by the same. Okay, questions so far on this? Okay, let's write the equation of the other one and then we'll draw our pictures. So this is glucose, which is a type of sugar. Okay? So the difference at the molecular level is they both dissolve. But sugar, when it dissolves, is still C6H12O6. It doesn't break apart as a molecule. So we just label it as C6H12O6 aqueous. Oh, sorry, I forgot to put the water above the arrow here. Okay? Alright, let's draw some pictures to help make it even more clear. Okay? So on this side, we need to draw Na+, separate from an SO4. Okay, so I'm drawing them all separate because this is showing them in water. Okay? Now, the reason why this one gets pulled apart into its different pieces, so this isn't before, but in water it gets pulled apart into all of its pieces, is because of what the water is doing. Okay, so we're missing the water in our picture here, so let's draw water now. Okay, so we're going to draw water, so water's H2O, but in these types of pictures, we're going to always draw it like Mickey Mouse, because that's what it looks. Because water is 2 H's as an O, and its molecular shape is bent. So the hydrogens are always bent up, so it looks like Mickey Mouse. You want to make a little code off to the side to remind yourself, like, this is water. Okay? Now, this thing is positive. Water is a polar molecule, as we've learned, and because it's polar, it has positive and negative sides. So, as anything that attracts, if this is positive, it can be attracted to the negative side of the water, and so water is surrounding this molecule, which is how it gets pulled apart. Now notice that only the oxygen is attached to the sodium because positive and negative. So on this one, how should I draw my Mickey Mouses?
The other way.
Yeah, ears first. All right, so on this side, the positive now I'm just showing enough to show that it's surrounded. Doesn't really matter exactly how many, just show it's surrounded. Obviously in real life there's zillions of water, right? Because there's no empty space, right? But we just want to show it's surrounded. So then on this side, since this is positive again, so this is why the ionics conduct electricity, is they get pulled apart. You now have positive and negative movement to pass the electrons around. Okay? Right? We'll play with these next time, but like with our little water molecules here, you can see that with the shapes, right? That the white connects to the green, but the red connects to the blue based on their differing charges. So imagine they were together, but when I drop them in water, there's now hundreds of Mickey Mouses, and they just start coming in and
It's highway robbery.
okay? All right, questions on this picture? Now the difference here is sugar is covalently bonded.
Why are we still in the robbery?
Okay? Now it dissolves because it is a polar covalent, and like dissolves like. But it doesn't break down the actual molecule itself. All you're seeing with dissolving is pulling apart sugar molecule from sugar molecule. So we're going to draw it very simple here, but this is in a sense what it would look like. Is you just have these giant molecules separate from each other. That's how the dissolving is happening. Now the water is interacting with them because sugar is a polar molecule. It actually also has hydrogen bonding. Okay, we're drawing them very simple here because it's a complicated Lewis structure. So for simplicity's sake, we're going to say, let's say this end of the molecule is negative and that side is the positive side because it's polar.
Yes.
But what's the difference between being polar and being ionic, positive and negative? Good, Christina. It's one thing that is positive and negative. Ionics are two separate, like, you have one positive thing and one negative thing. Everyone see the difference there? Versus like positive and negative as one versus separate positive and negative. So the water interacts with it just like before, right? Where you can have the little Mickey Mouses attached to that side, the face is attached to that side. That's how they pull the molecules apart. But the water cannot penetrate inside the structure itself, right? It can't break the molecule apart. And so this one does not conduct electricity because you don't have separate positive and negative movement. Questions on either of those pictures? So homework tonight, 3.7 is all of the math side of what we've learned, and then 3.8 is more like the visual side of solutions. Okay? We have 2 minutes to spare. Okay, so I'll pass you a ticket. If you have a ticket, yeah, you can stop me down.